join it. It's like I finally meet the names in my conferences, in my references in person. Today I'm going to talk about the resource theory of quantum metrology, and that would be my our ambition. So we only have reached a very small step here for a very
Okay. We should wait, and I'm glad to see all you here until the end of that day. So I thought it's quite unusual. So I think it's a nice conference and nice talks.
There'll be food afterwards.
Oh, such a spoiler, man. Well, I actually just sent an email to everybody, just, to prevent you from just going away.
I still not mentioned, just to prevent everyone from leaving.
Yes.
Is there drinks too?
Yeah.
Is there drinks as well?
Oh, of course, yes.
So there's drinks and food
Yeah, what I'm talking about. Drinks, soft drinks as well, and some small foods. Just happens like back at the room. So I'll mention that in the closing remark. Okay.
Okay, good. Feel bad. Yeah.
really sorry about that. So we can start from a very brief introduction to the general setup of the parameter estimation. In this task, the parameter zeta is encoded in a quantum channel, and the task here we want to is to estimate the value of theta. So in general, one put a probe state into this channel, and in the output, the state depend on theta. And after that, one can do some post process, including measurement and estimation, to evaluate the value of theta. So in unbiased estimation, there is a famous bound called Cramer bound. It gives the lower bound for the variance of the evaluated value of theta. And this F means quantum Fisher information, and it is a function of the output state rho theta. And if the post process is optimized, this bound can be reached. Therefore, quantum Fisher information effectively quantifies the ability of rho in probing theta. So quantum Fisher information have been employed to quantify the resource for about decades or several years. Here I only list a few recent results. In this paper, quantum coherence cost under translationally invariant operation is proportional to its quantum Fisher information in phase estimation. And in another paper here, it states that for any quantum resource, one can design a metrological problem where this resource is helpful. On the other hand, in quantum metrology, people are thinking about what is the quantum resource underlying this process. Ever since this seminal paper on quantum metrology. And here, one example is that one consider n-qubit state rho, with each qubit transmits through a phase gap, and one wants to estimate the value of phi phase. So if the state rho is in a GHZ state, which is essentially the maximally entangled multiqubit state, then one can reach the so-called Heisenberg limit, which cannot be reached classically. So therefore, after this paper, for several years, people tend to think entanglement is a resource underlying phase estimation. And then people realize that there are some quantum enhanced parameter estimation which without entanglement. And if you are interested in this point, I may refer you to this review paper. So here I want to say is that the resource underlying quantum metrology is really vague. So we want to establish, or we want to give a recipe to establish a quantum resource for metrology. Yeah. So here comes the general formalization of resource theory, and everybody knows it. When you really start from a set of states, which we call free states, and these states do not contain certain quantum property, and we are also interested in the mathematical structure of the state because when they are convex or non-convex, we have different results. And then for operations, the minimal requirement is that they cannot create coherence, right? And after that, one can measure the resource of, one can give the quantification resource as measure resource. And if we want to propose a measure, it should satisfy basic properties such as faithfulness, monotonicity, and it better be computable either numerically or analytically. And then when it comes to the application, we usually fit the resource to exist task. And most of the time we find they do not fit very well. So a smarter way is that people design tasks for given resource. But if we care about a specific task, maybe these tasks are not the same with the task we are considering. So our naive idea is that whether we can start from specific task to build a resource theory. This specific task can be realized using some resourceful state. So the power of quantum states in completing the task, we define it as the resource, the measure resource. And from the measure resource, we can define free states as those useless in the task, and free operations are the minimal requirement for the free operations as they do not increase the measure. So far, it's very easy. So the problem is whether we can apply it to a real task. And it turns out that everything is ready for parameter estimation. So in parameter estimation, we have task here to estimate the parameter theta. And we want to know what is the resource in the probe state. And the quantity of completing the task, we have already the quantum Fisher information of rho theta. So the measure resource in rho, we just define it as the Fisher information of the output state. And from the measure of resource, we can define the free states, which have zero Fisher information, and which is equivalent to that the output state does not depend on the parameter theta. And then it comes the free operation. We define free operations as those commutable with the parametrized channel. And whether it satisfies the monotonic property, we can prove it by the monotonicity of quantum Fisher information. If we apply this free operation to a resourceful state, the resource in lambda rho can be written as this, and using this commutable relation, we arrive this equation, and using the monotonicity of quantum Fisher information, just the post-process cannot increase the Fisher information. We can have this. And finally, this Fisher information of rho theta is just a resource in rho. So the resource is monotonic under this state of free operations. And then we can define a selective version of this free operation, which means that there exists a set of cross decompositions for the channel, and each cross branch satisfy this commutativity condition. Why people are interested in the selective version is that one can think quantum channel as measurement, and if we know the measurement, the result is the channel is still free. So people are also interested in the selective version of the free measurement. So this is this completes the recipe to build the resource theory for quantum estimation. So whether it can work good, so we apply it to some straightforward phase estimation task. For phase estimation, the quantum channel can be considered as a free evolution under Hamiltonian H. And the parameter we want to estimate is the action time t. And we put this input here, and in the output we get this state which depends on t. And for free operation, the output is for free states, the output state does not depend on t, which means they commute with Hamiltonian. And for free operations, they should commute with ut, which essentially translationally invariant operations. Therefore, if we apply our recipe to phase estimation, we find the free states and free operations coincides with U1 symmetry. Therefore, we can say that U1 asymmetry or energetic coherence is a resource for phase estimation. And if we apply our scheme to depolarizing estimation, the result is also straightforward. The only free state is the maximally mixed state, and free operations are unit-hole channels. So this free states and free operations just coincide with resource theory of purity. Therefore, we can say that purity is a resource for depolarizing estimation. So far, so good. So we want to apply this to our dephasing channels. A quantum dephasing channel can be defined as this. On qubit, it can be defined as this. And theta is the dephasing rate, which is a parameter we want to estimate. Here we consider this n qubit region, and with each qubit we transmit it through a phase damping channel, and in the output state we can get this output state, and here h xy means the Hammond distance between the two strings. xy are two strings of length n, and Hammond distance means the number of positions where the corresponding bits are different. Yeah, so that the output state can be written as this. Based on this, we can give our framework resource theory for phase damping estimation. The free states, it is easy to see that free states are just incoherent states. And free operations, we can define two types of free operations. The first one is they commute with phase damping channel, And the second one, they selectively commute with the phase dimming channel. For the first operation, we can give its explicit form. We prove that it is the Hammond distance preserving channel, which is defined as this. Essentially, if we start from coherence between x and y, and we want to end up with coherence in I and j, it should be satisfied that the Hammond distance between x and y should equal to I and j. So we prove that our first free operation is just equal to this Hammond distance preserving operations. And then by using this proposition, we prove that under Hammond distance preserving operation, the state transformation should satisfy this inequality. And for qubit system, this inequality can be satisfied, but for n-qubit state, it cannot be satisfied. So here comes our second set of free operation, which is the selective one. We prove that it is a selective version of Hammond distance preserving operations, and we can give the explicit form of cross operators of the selective version of Hammond distance preserving channel. And based on this, we can prove that n-qubit uniform superposition state as a golden state in our result theory. Yeah. So, so far we have discussed the free states and free operations in our result theory. Now we compare our results with coherence. Our free states are the same with coherence, so we compare the free operations. Here, DIO means dephasing invariant operation, which means the channel is commutative with completely dephasing channels. And SIO in coherence theory means selectively commutative with completely dephasing channels. And our free operations here, because here we need this equation holds for any p, and this will only need it hold for p approaches infinity. So HDP is a strictly subset of DIO, and our second type of free operation just lies in this intersection. We prove this scheme by give examples of states in each area. So we can prove this for m-qubit states. And for single qubit states, these operations collapse. So there are a lot of similarities with between our result theory and coherence. But there is an essential difference in that the off-diagonal elements in coherence theory are usually taken equivalently, but they are different in our result theory. For example, we can define this Hamming mode, which is defined as this. And if we take 2-qubit state as an example, the matrix element in the same Hamming mode have the same color. So let's say this more easier example. Here, psi 1 and psi 2 are usually considered have the same coherence, but the Hammond distance between 0, 0, 0 and 0, 1 is 1, And the Hamming distance between 1, 0 and 0, 1 is 2. So these two are different, have different results in our resource theory. And if we compare our resource theory with the Xueyuan symmetry, we can get this. In Xueyuan symmetry, one cares about the so-called coherence mode, where this x and y, the summation in this x and y satisfy ey minus ex equals omega equals to a fixed number. So this is all these off diagonal elements are in the same coherence mode. And in our resource theory, we care about the so-called Hamming mode. Let's take this 2-qubit states as an example. Coherence mode can be plotted as this, and the Hamming mode is like this. And this state, psi 1, is a superposition of 1, 0 and 0, 1. 1, 0 and 0, 1 essentially have the same magnitude. So in the resource area of Xueyuan symmetry, it has 0 resource. And psi 2 here is the superposition of 0, 0, 0 and 1, 1. And it has a maximal asymmetry in 2-qubit state. However, we can transfer these two states by the free states in our resource theory, which means the two resource theory are very different. They are very incompatible. So here comes the conclusion. We build a general recipe for resource theory of metrology, and we apply it to the resource theory for dephasing estimation. So that's all. Thank you.
Thank you for the nice talk. So we have time for a couple of questions.
Yeah, thanks for the really nice talk. What do you think would happen if you go to multi-parameter estimation? Like, so I can imagine that if I have a qubit state and I'm trying to estimate, say, 3 or 4 parameters, there might be no free states. Like, it might not be possible to define a free state in that case. Do you agree, or?
Yeah, we are figuring out this problem. And if we consider multi-parameter estimation, the free states may be very, very small. Yeah. So it may not work very well.
Probably not.
Yeah.
Hi, I was wondering if in the resource theory picture, there was a nice way of understanding when you can achieve the Heisenberg limit.
That's a good question. No, I don't have a quick answer.
So I guess I have 2 questions. First, kind of relates to that, which is there a notion of the most resourceful state in your picture, which I presume would achieve the Heisenberg? But do you have a notion of the most resourceful state? I mean, for many metrology problems, you can immediately think of one, right? Like in the case there, you have a 0, 0, 0, 0 plus 1, 1, 1, 1, which is kind of a null state that works in your picture. But have you thought about the most resourceful state?
Yeah, the most resourceful state for dephasing estimation is just the equal superposition of the maximally
And
coherent
I
state.
think those in general, you should be able to prove that they reach the Heisenberg limit.
But in phase estimation, one cannot realize the Heisenberg limit.
Okay.
Yeah.
The second question is that the resource theory, these examples you gave me, those remind me of the resource theory for quantum macroscopicity that was, I think, developed by Benjamin Yard and the Black-Vidal a little while ago. It also uses Fisher information as a quantification. Of course, their motivation was entirely different. They were trying to find out what is a macroscopic coherence versus a microscopic coherence. So when you have distances between these, like the Hamming distance that you have, then they in essence more macroscopic, like you're pulling the two cats apart. But are you aware of the macroscopicity? No. Okay, I'll point you out to some publication. I think there's an interesting link there. Cool. Thanks.
Okay, then due to the time limit, we can move to the next topic. Next article again.